In this video, we're going to be going over power amplifiers and power amplifier topologies. I apologize. Well, I don't apologize, but I'm wearing glasses. I've been doing drywall work and I've been sanding, and just it's bad for contacts. Drywall and contacts don't play nice together. So I'm giving my eyes a break doing glasses now. Just in case you thought I was perfect in every way. My vision, I am nearsighted. Other than that, I'm perfect in every way. But okay, so the amplifier basics. So we've been talking a lot about op amps. Op amps are really cool amplifiers, but really op amps are prioritized to having excellent, near ideal performance parameters in regards to things like linearity, speed. We'll talk a little bit later about things like gain, bandwidth, product, but so speed, linearity, very small input currents, or very small input current and voltage offsets, very high loop gains, things like that. These are the parameters that op amps are usually optimized for. They're usually not optimized for outputting a lot of power or for outputting a lot of high. There's easy ways we can modify op amps to have a high output power stage. And one of the things we talked about with op amps is feedback cleans up distortions in the output. So any feedback that happens after the input stage, feedback helps clean that up. And so one easy thing to do is we can just take an op amp and have it drive a power amplifier stage, and then take the output from that and feed it back to the op amp. If it's an inverting power amplifier stage, we want to feed it back to the positive terminal. If it's not inverting, we want to feed it back to the negative. But this is exactly what some op amps do. So TI's ALM 2402 is literally just this. It's just an op amp and then a power output stage. And it even lets you sort of separately power that output power stage. And then you just feed back after that. And so it's less ideal. But, this op amp can output, I think, an amp or 750 milliamps or something. So which is considered high power. Usually anything over 100, anything over 50 milliamps or so is usually considered a power op amp. So we can do this. This is one option. But historically, people have had the need for producing gains, power outputs that are much higher than this, even higher than 750 milliamps or so of current. And most of this has to do with radio and audio technology. So so radio and audio technology quite often needs to produce a wave that has a lot of power. So, if you're trying to communicate with a satellite, you might need thousands of watts of power. If you're trying to produce audio, a standard, theater will have 20,000 watts of audio easily in it. So we're talking very, having to take a signal that's fairly needs to sort of be maintained with fairly high quality. Our human ears are very sensitive to small changes in an audio signal. So you need to maintain a fairly close match for your input signal, maybe with some gain, maybe with some offset, but you need to drive this with a lot of power. You need to have a huge amount of power output. And that's where power amplifiers come in. And that's the purpose of this talk today, is to go over some of these different ways, different technologies we can use to amplify a signal to produce a lot of output power. And what are the pros and cons of different approaches? And one thing I want to mention too is op amps, which are typically designed to operate at 1 megahertz or higher, usually outside what's necessary for audio. Adding these extra power amplifier stages can create a lot of issues with these. So they can create, the biggest thing is a power amplifier stage typically will have some delay, some time delay through it, which can cause a phase delay, which can cause instability. So anytime you shift the phase of your signal in your path, as you'll talk about this a lot in the follow-up class to this, but anytime you get a phase shift in your signal, that contributes to this phase shift in feedback, which based on phase margin could create an instability in the overall feedback path, or it could create an instability for certain frequencies of the signal. There's a big reason why we quite often choose BJTs instead of MOSFETs. And that is BJTs have very small input capacitance versus MOSFETs. MOSFETs have a lot of input capacitance. And so having that op amp stage drive a capacitive stage can additionally create issues with stability, phase shift, feedback error, things like that. So, and a lot of, we present these things simply, but there's a lot of engineers that spend a lot of their life down in the weeds of trying to make little small changes to improve the performance of these amplifier designs. So complicated feedback networks that compensate for some of these issues, especially feedback networks that create negative capacitance. And we've talked about kinds of ways to create negative impedance, things like that, to correct for some of these issues that are created by power amplification. I mean, there's people who've made a whole career out of this sort of stuff. So, but we're just kind of scratching the surface of this field. So let's talk about amplifier efficiency. One of the most important things we're going to talk about today in terms of choosing a topology or the various pros and cons of these topologies is efficiency. Efficiency is the ratio of power dissipated by the load to power absorbed from the supply. So it's basically saying what fraction of your power is actually going to your load versus the fraction of your power that is just kind of I kicked something I wasn't supposed to kick, versus something that's just kind of burned away due to the internal construction of your amplifier. And it matters for more than just power efficiency, right? This isn't just a matter of, we're going to save the turtles and we're going to, not turtle, I guess turtles. Yeah, well, turtles, people like, nobody hates turtles. Actually, funny story. When I was a kid, I wanted to get a turtle really bad. And I wasn't allowed to because my little brother was afraid that if somebody stepped on it, the turtle would ricochet back and forth and it would hit people and make them small like in Mario. So I couldn't get a turtle as a kid. I can get a turtle now because I'm an adult. I can, but I don't, because I'm not living my life to its fullest. So there's that. Why do I do this to myself? Whenever I do these, I get all existential and sad. I have all this cool stuff, but I don't have a turtle. So All right. So power dissipation is not just about saving energy. It's not just about, saving money from the power company. It's also about, there's something, you got to do something with this excess heat. So if you have an amplifier if you have a 1,000-watt audio amplifier that's 70% efficient, well, you got 300 watts that are going to just wasted heat, and you have to do something with that. So if you look at like audio amplifiers in cars, typically they're these big, giant extruded aluminum housings. There's these massive amplifiers, and these are electronic. So you might say, what the heck is inside? Why do you need to have this thing that's like 2 feet long? It's like 20 pounds of aluminum. It's not because the transistors are that big. The transistors are the size of a nickel, right? They're not particularly huge. It's so big because it needs to dissipate that heat. And so, improving efficiency in your amplifier design allows you to not have to deal with dissipating quite as much heat, which allows you to make a smaller design, which allows you to save money on aluminum, and also, also save the turtles or whatever. So anyway, just think about that. Power efficiency is not just a matter of saving money on the power bill. So the first amplifier topology we're going to talk about is Class A. Class A amplifier is fairly straightforward. This is basically just a biased BJT, so you have this BJT providing a gain. As your signal goes up, the current through the BJT increases. As your signal goes down, the current through the BJT goes down. And so, this design is this is sort of if you had to just design an amplifier, you might come up with this. And these are great. I mean, they're great in terms of their BJTs. If they have fairly linear gain operation, this is a very good way to get a lot of, to get a high fidelity reproduction of your input signal. What's the downside? The downside is this is always burning current. So this is operating in its sort of half signal mode. And this is drawn not quite correctly, right? So really this should be kind of, right? So this is, at mid wave here, this amplifier is producing a lot of current. And typically how would you get from this to this? You just add a capacitor. So typically if we had a capacitor here, that would cut out the DC. Using a capacitor to cut out the DC is a fairly common technique. You got to be careful though, because it's got to be a big capacitance if you have low frequency DC. So if you want to, a capacitor is great for cutting out DC because to low frequencies, a capacitor appears as an open circuit. To high frequencies, it appears as a short circuit. But especially when it comes to audio and you're dealing with things like 20 hertz 20 hertz is fairly close to the DC. So if you want a capacitance that looks like a like a short circuit, it looks like a wire to 20 hertz signal, that's got to be a very big capacitance. So you have to be careful with that. But you know, that's an easy way to do it. But the key thing here is this is always burning power. So when there's zero input signal, this thing is biased halfway and it's burning, you know, it's just burning, it's just, you know, burning current. So low distortion, which is great for class A, very poor efficiency. Because, you know, even if you're amplifying a quiet little whisper audio signal, it's burning power to do that. So the biggest reason it's doing that is because we have one transistor operating over the full range of all the highs and all the lows. Still have to keep this transistor active. It's never turning off, or it's kind of almost turning off at the very bottom trough of the very smallest signal, but it's always on, always operating. One way to fix that is to go with sort of our standard dual transistor designs, and you've seen these a lot. These are used, you know, they're used all over the place. And in this design, basically, you have a signal where when the signal is zero, both of these transistors are turned off. So it has the advantage of it turns off both transistors to produce a zero, and it turns on the high one to produce a higher signal, and it turns on the low one to produce a lower signal. You know, when I say zero, I mean mid-rail, right? Whatever that is. You know, all of these amplifiers we're talking about, they might not be shown with a negative rail, but so they might be producing a signal that's nominally something other than 0 volts. But again, this is usually, it's easy to get rid of the DC offset using a capacitance or something like that. So I'm just going to call it 0, right? 0 meaning 0 signal, not 0 volts necessarily. So at 0, both of these are off. So both these transistors are off, and so it's not burning any power. And that makes this design have good efficiency. But the issue is it's got a lot of distortion. It's got a lot of distortion because when it switches from this one being active to this one being active, as it goes through that transition, it's operating in a very highly nonlinear gain range of these amplifiers. As you get close to the threshold voltage of these BJTs and of MOSFETs, they become highly nonlinear. They become, you know, they sort of get, you know what the curve looks like, right? It looks like, you know, kind of like, right? So you get, when you're in this range, it's not a nice linear one-to-one amplification, and we're using that range for these types of amplifiers. What do we say here? Active devices conducts for half of the complete cycle of the input signal. Well, it basically means for the upper half of the signal, this one's on. For the lower half of the signal, this one's on. So class AB. So the issue we had with the previous amplifier was it goes through this middle, as it gets close to that crossover point where it switches from one transistor being on to the other transistor being on, it has this highly nonlinear region. Class AB amplifier biases these so that it biases these inputs so that when we're in that crossover point, rather than both turning completely off and having all this high nonlinearity distortion, they both sort of stay on through. So basically there's this window in which both transistors are sort of mildly on. So basically instead of having one curve go like this and one curve go like this, what we're doing is we're biasing these a little bit in each direction so that one kind of goes like this, or one kind of goes like this, and one kind of goes like this. And then when you combine these two signals together, you get something that looks a little bit more, you know, maybe a little distortion in the middle, but a little bit more, right? So we are using diodes or bias resistors or something to produce this sort of voltage offset between the signal seen by these input gates, by these input base inputs to these BJTs. And as a result, we get more linear behavior. You know, we're sort of cutting out that awkward both turn off region, and that's nice for linearity. The problem is we have this little region where both of these are conducting. So when we're close to 0, we have this issue of both of these transistors are mildly turned on, which means they're burning, they're essentially creating it's resistive. It's not like these are not, low resistance at this moment when they're very close to the threshold voltage, but it's still creating a pathway between the rails. So it's going to burn current when it gets close to zero because they're not going to both fully turn off. So class AB is sort of this way of achieving slightly better linear performance at a cost of our crossover region has both transistors on at the same time, and also at a cost of you kind of have to burn a little bit of current here sometimes to produce this bias signal or to produce this adjustable bias signal here. So I want to zoom in a little more to talk about why this conduction phase matters. So we say this device conducts for more than, I didn't talk about this, I should have. This conducts for more than half, but less than the complete cycle of input. And what that's saying is that because of this bias voltage, both of these transistors stay on a little bit into that crossover point. So the top transistor stays turned on when in the previous case, it would have fully turned off and the bottom transistor had turned on. So the high side transistor stays on through that crossover point. The low side transistor also stays on through that crossover point. So they're slightly more, so they're both on. They sort of hand the baton off in the middle somewhere where they're both on. And that's kind of what we're saying here. And just to show this a little bit better, and I kind of already do this a little bit, but if you look at, this is kind of a, an exaggerated drawing of it. If you look at this kind of dead zone, which is between this silicon threshold voltage, 0.7 volts shown here, which is implying silicon. And, this nonlinearity at this crossover point will produce, if you have an input audio signal, it will produce this dead zone. And you might say though, like, who cares? If this was a 1 kilohertz signal, even with the dead zone, it's still going to be a 1 kilohertz signal, right? I mean, the frequency, the peaks are still going to be there. It's still going to be the same thing. So why do you care? Well, the reason you care is think about what distorting a sinusoid means. If you have a sinusoidal signal that's 1 kilohertz, any distortion to that sinusoid, any deviation from a pure perfect sinusoid, what does that do? If you consider the series expansion of any function, what is the series expansion of a perfect sinusoid? It's one term. It's one term at that frequency of that sinusoid. What does any distortion to that signal do, to that periodic signal? It creates, and if you think about it in terms of the series expansion of the function, it creates energy. It creates magnitude for frequencies that are harmonics of that intended frequency of amplification. And it turns out our ears are actually very sensitive to that. So when you distort a signal, creating all of these harmonics of that primary signal, we can pick it up. Our ears are very sensitive. Not only that, but if we were doing a radio application, that distortion of a core radio transmission frequency is going to produce harmonics that are going to be put out on the radio spectrum that could be illegal. So it could be, there's transmission on the radio spectrum is heavily regulated to prevent things from interfering with other things. And so if you are if you're outputting energy from your radio transmitter at harmonics of your intended frequency, it's very likely some of those harmonics are going to be possibly interfering with other systems that are trying to operate on those higher harmonic frequencies. So we really want to avoid this, and I really want to stress our ears are very good. Humans, our senses are not great, right? I mean, our sense of eyesight, we got to fix them with little shards of glass here. But one thing we're good at is hearing. So humans have very good hearing, not only hearing in terms of we can pluck out a little tiny frequency, even in the midst of a much higher energy frequency at a different frequency. I'm using the word frequency too much, but our brains are able to kind of filter audio to where we can really tune into specific frequencies. We can hear somebody whispering next to us, even in a room, in a noisy room. Our ears are just very good at plucking out, say, audio signals. And the flip side is they're very good at hearing even small distortions to audio signals. So if you really want to produce high fidelity audio, you gotta cut this out. You gotta make sure you're reproducing a sinusoid without all this extra noise. Okay. So what's a Class C power amplifier? This is sort of the last of the original core power amplifiers. This one is really basic. This one is a BJT that does turn off at 0 because it only conducts for half of the cycle. So this is an amplifier that leaves off the bottom half of the signal. And what's the advantage of that? Well, the advantage of it is it does turn off. So it's very efficient. The disadvantage is you're only getting half of the waveform. And you might say, well, come on, you can't just have half of the waveform. You actually have less than half the waveform because you have that plus 7 volt offset, right? You have this, so you have less than 1/2 cycle of conduction for this amplifier. But it's very efficient. And you might say, well, you just gave us this big long spiel about why avoiding distortion is critical. I did. But there are some times where you can clean up distortion after the fact. Let's say all you're trying to do is produce you just want to produce bass. You want to produce a 20 hertz tone, and that's all you care about, is producing just a ton of energy at 20 hertz. What if I use this amplifier to do that? Well, okay, I'd be producing a ton of energy at 20 hertz, but also a ton of energy at 40 hertz and a ton of energy at 80 and a ton at 160 and blah, 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 blah. But what if we had it as an output stage to this, a really good filter, and we just said, yeah, I'm going to use this amplifier. It's going to produce high efficient 20 hertz signal with a whole bunch of noise, but I'm going to use filters after the fact to clean all that up. I'm going to clean all that noise up afterwards. That's the idea behind a Class C amplifier. Class C amplifiers are almost always used in these rare cases where you need to produce a ton of signal with a ton of energy, and you can have filters after the fact that keep it all cleaned up. And sometimes you'll even just put them in here. So sometimes in here you can just do, put one of these, put an inductor, an LC filter in here, and sometimes you can have a tuned filter right at that output stage that helps produce a cleaner output signal. And so that's Class C. Class C is typically, again, it's used when you're trying to produce a ton of power and you have a way to filter it after the fact. So Class D, before I get to Class D amplifiers here, I want to talk a little bit about how these amplifiers we've been talking about produce a variable voltage output. So these are using BJTs. All the ones we've talked about are using BJTs, which basically, they limit the current between their junctions as a function of the current into their base. So they limit this collector emitter current as some gain multiplier of the base current. And so when they're doing that, they are produced, there's a voltage across the collector emitter of these transistors, and they are burning power. So, you have a current flow through a transistor with a voltage across its collector emitter terminals, and it's burning power. And that's what they do. These transistors, they're to produce a variable output voltage. There's lots of ways to think about it, right? But to produce this variable output, essentially you're burning voltage across the transistor, which produces heat, which is inefficient. And what we'd really like to, when we're trying to get really high efficiency, we don't ever want to operate transistors in this mode where we don't want to operate them in this mode where they have a large current through their terminals and they also have a voltage across their terminals, right? We don't want them being these power dissipating devices. We'd rather they just switch on and switch off. So, an on transistor, generally, fully on, as on as it can be, burns very little power. An off transistor also burns very little power. It's only in this middle window where transistors are producing heat, where they're burning energy, where they're a positive energy device. And so the idea behind a Class D amplifier is, can we produce a signal, an analog signal? Can we produce a variable voltage signal without having to operate transistors this way? Can we produce a variable signal without having the transistor operating in its linear mode? And the way that it's achieved with a Class D amplifier is through this concept of a signal being produced by pulse width modulation. And so I just want to talk about this before I get too far into the slide. I'm going to use some space up here if I can. Consider we have a system that's powered by 10 volts and we try to produce a 5-volt signal. Well, there's ways we could produce a 5-volt signal. We could take 10 volts and we could have something like this, and we could produce 5 volts here. Oops. And the way we did that is, right, we burned power. We had this transistor burn power here. But another thing we could do to produce 5 volts is, what if we just took the full 10 volts and we produce a signal like this? Now you might say correctly, that is not a 5-volt signal, John. That is a 10-volt signal and a 0-volt signal. And you're right. But the average of this signal is 5 volts. The average is 5 volts. And there's plenty of ways to get that average. So for instance, if we just low pass filtered this, it would effectively take the average. So we just ran this thing through an inductor, capacitor. What would the output look like? The output would look like 5 volts. And so the nice thing is, when it comes to generating an analog signal in this manner, our transistor, when it's producing these, is fully efficient. So we can use a MOSFET. These are fully turned on or fully turned off. And also this LC circuit, how much power does it dissipate? In the ideal case, none, right? Inductors and capacitors are purely reactive power. They don't actually dissipate real power. I mean, that's not actually true. They have some internal resistance and things like that. But in the ideal case, where we are producing a signal by having a pulse train whose average value is our desired signal, which then gets averaged by an LC filter, there's no inefficiency here. In the ideal case, there's nothing to consume power. The transistor is fully on, fully off, which is purely on mode, it's not dissipating any power. Purely off mode, it's not dissipating any power. It's using a filter that doesn't dissipate any power. So that's the idea behind this. This is the idea behind generating a signal like this without having inefficiency, without having power loss, without having heat loss, is this. And how do we actually do it? Well, the first thing it starts by doing is by taking our input signal and turning it into a pulse train. So what we want is very small voltages. We want very small voltages to look like this, right? A very small average value. And very big voltages we want to look like this. With a very big average value. And the way we do that is we simply use a comparator. So a comparator is, you can think of a comparator as just an op amp with no feedback. So basically any moment that the voltage at the positive terminal is higher than the voltage at the negative terminal, this thing's going to rail. And any moment the voltage at the negative terminal or the positive terminal is less than the voltage at the negative terminal, it's going to rail in the other direction. So what's happening here? So we have a triangle wave that's being compared to our input audio signal. What does that mean? Well, if we have this triangle wave like this, and what if our input audio signal is high? If our input signal is a high voltage, what's this comparison going to do? Well, when is the voltage of this positive terminal higher than the voltage of the negative terminal such that this thing turns off? Well, it's only here. Only at these little windows is that true. So the signal this thing is going to produce is going to look like this. Now let's take the other case. Let's say our signal is low. Oops. Put our triangle wave back here. Let's say our signal is very small. All right, now, when is the input at the positive terminal going to be bigger than the input at the audio input such that this thing rails low? Well, now all of this, right? This whole thing, in this whole thing, that condition is true. So this signal is going to look like this. So I hope that makes sense. So, but basically, we're using a triangle wave as a way of by comparing a triangle wave to our signal. When our signal is a high voltage, we're going to get this pulse train that has a bunch of wide pulses and these little skinny pulses, or sorry, little skinny zeros and fat ones, or sorry, skinny 0 voltages, fat high voltages. And when our signal is small, we're going to produce these skinny high voltages and fat low voltages. So once we've created that pulse train, now it's simply a matter of amplifying it. So now amplifying these pulses is fairly easy. We can just run this thing through an inverter. So we can, so this is gate drive amplifiers. As I mentioned before, the gates of a MOSFET are capacitive. So usually you want to have an amplifier that can produce a lot of current initially to charge those gates up or discharge those gates. So usually when you're driving MOSFETs, if you want fast on-off performance, you do need a gate drive amplifier. Okay, and possibly, so I describe this in terms of this being an op amp. If this were actually a comparator, we may have gotten negative behavior. So we may have gotten, so an actual comparator would have output high when the positive was greater than the negative. And oh, that's the way an op amp would work too. Sorry, I think everything I just described was inverted. Sorry, I think everything I just described was backwards. So the big fat pulses, sorry, the big high pulses and the skinny low pulses should actually be flipped. It's going to be the inverse behavior. You could have been watching the video and you're like, John, what are you talking about? When the voltage here is higher than this, it's the other way. So anyway, so this possibly inverts the pulse train, but then it goes into this inverter stage, which inverts it again. So sorry, you got to pay attention to whether we're inverting the inverse or not. And so this is just an inverter. It's an inverting amplifier that if we choose MOSFETs that are high current, this can produce a huge amount of current if need be. And then what's happening? So we're amplifying this. So instead of just being this little signal pulse train, now this is a power drive pulse train. This thing is capable of producing possibly huge amounts of current. And then over here, we have a LC filter, which, what does that do? It gets rid of this, right? It takes this and converts it to this. It takes this and converts it to this. It gets rid of that carrier frequency. It gets rid of that chop that we use to produce the pulse wave, the pulse train. And then see out, this is, everything described here is powered by 0 and VDD. So which means that it's going to sort of be offset. This capacitor see out eliminates that offset once again. So it basically, our signal doesn't have a DC offset going through a capacitor. And then this is just a load. Let's talk a little bit more about that C out though. So again, having this capacitor here is a way of taking a signal that kind of looks like this and converting it to a signal that effectively is like this, right? So it cuts out the DC. Again, a capacitor looks like an open circuit to DC signals and a short circuit to high frequency signals. But this is not super efficient. So in this case, what was our signal limit? Our lowest signal was 0 volts. Our highest signal was 5 volts or whatever. Let's say VDD was 5 volts, which means after we did this reconstruction, we'd be at 2.5 and negative 2.5. And we want this for audio. We want to be able to push and pull the speaker. We don't want to have a speaker that only is able to push out. We want to push and pull. We want to use the full range of motion of that physical speaker membrane. So we kind of want this, we want this current flowing both directions. We want that behavior. There's another way we can get it though, and that's with what's called an H bridge. H bridge is effectively you drive both sides of the speaker. So we are inverting, we're taking our signal that we're using to drive and we're inverting it and putting that on the other side of the speaker. So we can drive both sides of the speaker. So when we want to get a high signal, we can drive this side to 5 volts and this side to 0 volts. When we want a low signal, we can drive this side to 0 volts and this side to 5 volts. And this full bridge amplifier, by being able to drive both sides of the speaker, in the previous case, one side of the speaker was just connected to ground. And that's why we're limited like this. In the case of a full H bridge, where we're able to drive either side of the speaker, if we drive one side 5 and the other side 0, or the other side, one side 0 and the other side 5, that's a full 10-volt swing. So now we're able to produce, not only using this by driving both sides of the speaker, not only are we able to avoid having to put this capacitor in there to cut out the DC, but now we're also able to go full differential. So we can go 5 volts, negative 5 volts. So we're able to produce a potential in either direction across the speaker that goes the full range of our signal driver. So I'm messing this up now. Basically, if one side is pinned to 0 volts, if one side's pinned to 0 volts, then you're very limited in terms of your total range of differential voltage you can apply. If neither side is pinned and you can drive either side to 0 and the other side high, you're effectively doubling your range of potential. You're taking a single-sided supply and you're effectively creating a differential supply out of it with twice the overall magnitude. So that's neat. That's nifty. Oh, efficiency comparison. Yep. So one more thing, we kind of already talked about this, but Class D is typically considered the most efficient. Class Cs can be very efficient, but A, very inefficient, very good fidelity. B is very efficient or more efficient, but pretty terrible quality. AB is sort of a nice in between. C is sort of just used for power, where you can have a filter that cleans it back up. And then Class D, which Class D is really pretty much the only thing people use nowadays. That is the most efficient. The problem is it does need that reconstruction filter if you're trying to cut out these high frequencies. All right. Thank you, everybody.